Hello, Math 1. Today we are going to work on applications of quadratic functions. This is the very last piece of Module 7 and probably the most important. Very common problems we run into with motion and geometry and things like that, so that's what we're going to talk about. I want you to put away any preconceived notions of word problems that are hard, because application does mean they're going to be word problems, because I think you'll find some of these quadratics are fairly I guess you could say, easy to visualize. Let's take a look at some of these. Now, what I've done is I created a Google Doc, and again, if you're taking notes, just kind of pause the video as I go. So I gotta kind of keep these videos short. All right, so there's going to be a series of these actually. So part one, we're going to deal with motion. I think we got geometry, then some number theory. All right, so one of the applications we run into commonly with these quadratic functions is motion. And a typical problem reads like this one. Alex hit a volleyball into the air with an initial upward velocity of 24. Now that number, when they give it to you, it sounds like it's going to be part of the problem you're going to use, but it shows up right here. Okay, the height of the ball h, the height in feet of the ball above the ground can be modeled by this function. It gives me a quadratic function. You need to be able to spot that it is quadratic, where t is the time in seconds after Alex hit the volleyball. All right, and I tell a lot of people this. The very first thing you got to do when you read a word problem like this or an application problem, they give you an equation. You got to classify that equation and say, well, what type is it? And as soon as you see this squaring term, and it's your highest power in the function, it's a quadratic function. And when you think quadratic function, you need to be thinking, I could have to deal with a vertex, x-intercepts, it has a max or a min. All those things need to come into play. Okay, so we're going to take those and figure out what exactly, it depends on what they're asking us, so we'll use that information accordingly. And like I said, that 24 can confuse you. It doesn't show up except for right here. That's your initial velocity. So when you take a physics class, you'll see those things. Acceleration due to gravity, initial velocity, and that turns out to be the initial height. Okay, all right. So the very first thing you got to do is decide, what does your function do? And your function has an input and an output, just like any other function. And your input, it turns out, is time. You put things in for t, and it tells you a value for h. So I'm going to put time is my very first thing that I'm worrying about here, okay? And I don't want that to be that, and I don't want it to be bold. Output is height, and it's h, right? I guess we could have put equals there, couldn't we? So we know what our function does. You put a time in it, height comes out. You can't put a height in this function, it won't work. Okay, so let's go through here and see some typical problems that emerge and things they ask us to do. It says predict the height of the ball for some given time t. Probably the simplest question that you can run into. And in this case here, they're saying, hey, how high is the ball after a second? And that basically boils down to, what in the world? That boils down to just evaluating the function at 1. This is a time unit. It goes into the function. This function is built for those times. So you want to find h of 1, which is negative 16 times 1. I'm going to square that 1, although it's just going to be a 1. But just to show our work here, plus 3, and not equals 3, but plus 3. And I think that's going to be what? Negative 16 plus 8, 24. I think we're going to get 11 feet. Okay? So the answer to that will be 11 feet. That's the easiest question they could possibly ask us. All right? All right, let's check out another question they typically ask, and this is another one dealing with the same information. We got the volleyball, we got our function here. They want to know how high will the ball go and how long it'll take it to get there. Either one of those questions could be asked. It could say, hey, how long does it take the ball to get to its maximum height? Well, that's dealing with how high the ball goes. Now, the first thing is your vertex, in this case, is actually, let's write that down. Your vertex, in terms of units, is what? It's a time and a height. And right there lives that information they want to know. the time it takes it to get to the maximum height, we know it's got a maximum because A is negative, is here, and this is the maximum height. So they're asking me to compute a vertex. And we know that that's negative B over 2A, and plug it back in. And just to make this video a little shorter, I've actually got a Desmos open here, and you would too if you're on an exam or something like that. You could have a Desmos. And if I got time, I'll go back and do it by hand. But I've already typed it in. Notice what I've done different though. I didn't put T in here. You need to. I'm using X. You could have put Y equals, but the variable X seems to work better in here for me. So keep your variables Y and X when you go to your Desmos, and if you're in your calculator, it's going to force you to do that anyway, okay? So I've graphed this function, and if you realize what they're asking you, there's your information right there. It's that quick. It takes 0.75 seconds for it to get to a maximum height of 12 feet, and that's the answer to that question. I mean, that is that simple. You're looking at a vertex. So we would say it takes 0.75 seconds for the ball to get 12 feet above the ground. Okay, so that's the answer to that question. That answers both of them. And if we get time, we'll come back and do it by hand because you could. And I just want to make sure we don't run out of time on this. Okay, now, this one right here can be probably the more tricky question. And this says, how long will it take the ball to get to a specific height? And I didn't specify in this question because this is the one that can typically mess people up. Let's suppose for a second they want to know how let's make the height, for example, 10 feet. All right, so what a mistake would be here, and I see this all the time. A person plugs that 10 into their function, right? That's putting something in here that doesn't belong. This function does not take in feet. It takes in times. You can't plug a 10 into this. It doesn't even make sense. Instead, what you're going to need to do is say, wait a second, how long? This part right here, how long? That's telling you what you're solving for. You're solving for t, right? I want to know how long something is. That's a time. So we'll have to solve an equation. And it sounds like we need to know when the height is 10, and we've got to deal with a quadratic equation. Because that's what happens with a problem like this. And it probably is one of the more, I guess, more challenging ones for us sometimes. And we need to set this equal to 0, put it in standard form. And to be quite honest with you, I'm going to go to Desmos after that, and we'll wrap this thing up. So I'm going to put this guy equal to 0. And I know that that's not going to change this term, right? And we're just going to subtract that 10 from both sides. And that combines with the 3 to get me a -7. And that's going to be equal to 0. Okay? Now we'll go to my Desmos and check this thing out. So we want to know when, we're going to type in the related function. You know what? I'm going to copy and paste it right here and just change that to a -7. Speed me up just a little bit. Okay, when's that going to happen? Okay, so it's happening in 2 different places, it looks like. And remember, solutions are the x-intercepts. So it happens at 0.39 seconds. So it's 10 feet above the ground at 0.39 seconds. And it's 10 feet above the ground in 1.1 second. Well, does it make sense? Yeah, I think it does, because the ball goes up. Right, he reaches 10 feet. I guess you could see it right here too. Right, there's that number. There's that number. So that wouldn't be a bad way to approximate this, but this is exact down here. Or not exact, but pretty close. You can see up here, that's when this is happening. So you could have got it from there too. Anyway, that's the answer to that question. Anyway, don't forget to watch these videos before you try the problems in Delta Math. I've got you going to a series of these. Maybe the others won't be quite this long. I hope you found this helpful, and I hope you guys are being safe and staying healthy out there. I'll see you in the next video. Take care, Math 1.